Thank you very much for the invitation, Yak, and thank you everyone for joining. The topic of the series is perfect for some of the ideas I'm most excited about these days, so let's jump in. This talk is called Addressing Two Classic Debates in Cognitive Science with Deep Learning.
Oh, wow.
He's super good.
Before getting to the research, I want to highlight the key people in the lab who made this work happen. We have two postdocs, Amin Oran and Wei-Qin Bang, who are project leaders, and a number of other folks contributed important aspects of the work I'm going to tell you about. And as we all know, there's been remarkable recent progress in AI. It's hard to escape the headlines about the latest AI advances. So we have some headlines here: ChatGPT heralds an intellectual revolution, or meet Dolly, the AI that can draw anything at your command.
Brenden, you're not sharing your screen.
What?
At least I don't see it.
I see Brendan's screen very well. So I
Okay.
think the problem is probably on your end, Gary. Sorry.
I'm sorry. Ah, I see it now.
Okay,
Good.
great.
My bad.
So it's hard to escape these headlines about AI advances. And in terms of the technical advances, most have been driven by the transformer architecture, which is there on the right. So as cognitive scientists, researchers studying minds, brains, and machines, we should be truly interested in these developments and what they tell us about us as humans. But what can these AI advances really tell us about human learning and development? There are reasons to be skeptical of the genuine connection. For one, these AI systems are trained on highly unrealistic data sets. Web-scale data for AI versus natural experience for children, or for large language models, are trained on billions and now trillions of words versus the millions that children need to learn language. In terms of web scale, it's not just a matter of the quantity, but it's also the content. For instance, ImageNet, the most common data set for training computer vision systems, is 12% dogs. So that means there's 140,000 roughly different examples of dogs in the data set. It's 12% of what those models are seeing, which is just not realistic to the type of data children get when they're learning. And these AI systems are also limited in their abstractions and their generalizations. For these reasons, many researchers, myself included, have been dismissive of some of these AI advances for telling us much about how the mind works or how children acquire knowledge about the world. But my perspective on this is changing, and I want to tell you why. So in this talk, I'm going to tell you about our work in addressing two classic debates with deep learning. Debate number one is, what ingredients do children need to learn words? And debate number two, can neural networks capture human-like systematic generalization? So let's get into that first debate. And let's talk about the problem of word learning with an example inspired by W.V. Quine. So imagine you're in a foreign country, you see this scene, and you hear the word zup. So what does zup mean, right? What is the right visual reference? Well, it could be a ball, it could mean in this language a big ball, or maybe a ball on a carpet, or an object, or it could be a couch, or pieces of couch, or a pile of toys, or it could be the time of day, or the color yellow, or the particular location that you're in, or describing whether the room is messy or clean. There's a huge number of logically consistent hypotheses. It may seem like a contrived situation, but this is closer to what the world is like for a child learning their first words. And they have to solve this rather remarkably difficult problem. And given this difficulty, many have wanted to know, what ingredients do children need to learn words? What building blocks do you have to have in place to make real traction? And there's been a lot of different proposals for underlying ingredients and inductive biases. I have just a sampling of some of the famous ones, like the mutual exclusivity bias, whole object bias, taxonomic bias, shape bias, the ability to engage in joint attention or social cognition or reasoning in order to support language learning. I love all this work. Each of these ingredients really has genuine support in the literature, but it's hard to discern their relative importance if you posit a role, some role for all these mechanisms, but how do you know what's doing most of the work? What is really needed to learn words in the real world. So our plan here is we're going to leave these biases aside for now, and we're going to start simple. We want to know how far can a learner get with relatively simple domain general learning applied to a child's natural input. And we have 3 minimal ingredients that we're going to use to get this started. Ingredient 1 are going to be slices of one child's longitudinal first-person experience. So video with transcripts from what was being said to the child, but no extra labels, no direct supervision, no labeled images. Ingredient number 2 is going to be representation learning or feature learning, so learning high-level features from the raw input. And ingredient number 3 is going to be associative learning, close, but a little bit different for how it's often talked about in the world word learning literature, where we're going to start linking the visual features to the features of the language, the linguistic features. And at this point, I also want to say we're going to use the strongest algorithms available in machine learning rather than the most psychologically or biologically grounded. We can talk about the consequences of that, but in my view, it's not a stretch to assume that whatever the brain can do is better than today's algorithms. So with that, let's move forward. The data set we use is called SACAM. Here's a little sampling of it. The SACAM data set is from a paper from Jessica Sullivan and a number of other colleagues published in 2021 in OpenMind. So this was not our data set, but it made our work possible. We couldn't have done our research without it. We are incredibly grateful for this resource. If you haven't checked out the paper or the data set is available to researchers on DataBrewer, you should. It's a tremendous contribution to science, and we and others are only beginning to scratch the surface of what's possible with this data. And what's particularly unique about it is that it's longitudinal audiovisual recordings over 26 months from individual children. It's not a bunch of different children pulled together. This is 3 different babies. And the babies have up to almost 200 hours of video recorded in slices over the 26-month period from 6 months to 32 months of age. Baby S has almost 200 hours, and baby A and baby Y had a little bit less. 61 hours of that 194 hours is transcribed. So we're going to focus on baby S in particular, and we're going to call that data set SACAM S. And so in the data set, it was roughly 1 to 2 hours a week that was recorded. Now I'm going to tell you about the representation learning piece here. So this is what we're going to do with the visual data, how we're going to extract structure. And this is based on a recent article from Amin Oran, learning high-level visual representations from a child's perspective without strong inductive biases. It's in press at Nature Machine Intelligence. And I also want to call out Amin's GitHub page has all these models already available for the pre-trained models are available for download. So if you want to try experiments on these models, you can go to Amin's GitHub page. And here's how we do representation learning through the eyes of a child. We're going to take a transformer architecture for highly generic learning. And I'm calling that highly generic because it's state-of-the-art for images, for text, for speech, processing, and so on. The network summarizes an image. So this is the image. It breaks it down into patches and ultimately summarizes the whole image with a single vector. In this case, 768 dimensions, but that's not a particularly special number. And the best overall network that Amin trained had 85 million trainable parameters. So not huge by today's standards, but it's a sizable model. And Amin actually trained 48 different types of models, varying the architecture, the algorithm. Took 750 days worth of the best GPUs we have here at NYU to settle on this architecture. Here are some of the details in this bullet point if you're interested. And it's only using the static images. We haven't done as much as we'd like to with the video itself yet. So we're using those static frames and trying to learn a embedding that represents important structure in that image. So to give a very quick tutorial in transformers, if that's new to you, we can break the image up into these patches. And then each of the images is going to be summarized. Each of those patches is summarized with a single vector that is just going to summarize what you see in that particular patch, but it doesn't have the context around that patch. So you might not know if that's a body part or what body part it is or what that toy is. But then at the next layer of processing, you propagate that vector forward and incorporate context from all the other patches around it. And you iterate this process all the way up into the top, where you have these contextualized pieces of images. And all those parameters are trainable in order to try to fulfill some objective. The main objective self-supervised learning algorithm that we use is called DINO from Karen et al. And the key point is that two versions of the image should have the similar representation. So if you take one of the frames and you crop it in two different ways, or you do some colorization of the two different crops of the image, and then pass it through two copies of the network, they should have similar feature representations because they were produced, they're different views of the same underlying frame. That's the main idea. That's what the network is trying to do. And it's self-supervised in that it needs no category labels, no extra annotations that the child wasn't able to get. So both these copies of the network are going to produce an internal representation, which we're going to try to attract to be more simple. And our main evaluation technique uses standard linear probing as used in machine learning, where based on the baby's view, one baby's data, right? No other babies. And that's important because children must learn about the world and learn language from their own experience. They can't pool their experience with their friends and their siblings, right? So we're only training on one baby's data. And then we're going to freeze the features. So those 768 high-level features are going to be completely frozen. And we want to know with just a parameter, a weight for each of those features, so no new features, that's a reweighting of those high-level features. Can we say, get a cat detector that could reliably detect cats just by reweighting those high-level features and no new features? So that's the idea of the linear program. And we want to examine whether features are useful in a broad sense, and thus we have a broad range of evaluations. We have it labeled S, which is a labeled subset of the baby S's data with 22 to 26 different classes like car and hand and ball. We have isolated objects with white backgrounds. We have objects with various transformations. We have ImageNet. We have place classification. We also have some segmentation tasks that require sort of semantic segmentation of categories. And we have these 8 different tasks just because we wanted a broad view of what these features are capable of. But how well can we learn through the eyes of a child? This is a bird's eye view. A summary plot over there on the left shows the normalized score, normalized compared to the same algorithm, the same architecture trained on the ImageNet data set. So that's going to represent 100%, and this is going to be averaged over the 8 different tasks. And the DINO trained on ImageNet is not too far from a state-of-the-art vision model. So it's a strong vision model. And what we find here, so the ImageNet models are in pink, and the baby trained models are in orange, where the different letters of the different babies, or one combined across the 3 babies. With the baby S trained model, you can get somewhere across all the babies, really, you can get somewhere between 60 to 70% of the performance of ImageNet trained model using the baby's data instead. And if you compare to ImageNet models on decreasing subsets of ImageNet, they're on par with a model trained on about 10% of the ImageNet data set. If you also look at the green here, which is randomly initialized features, it's much stronger. You get much stronger features trained from the baby's view than you get from random features. So this is just to show you the breakdown over the 8 different tasks with now just the raw accuracies or segmentation performance on the y-axis. And I'm not going to dwell on it, but if you look at those black dots there, that is comparing the baby S model to the ImageNet 10% model. So baby S model is a little bit better when tested on classes from that data set, right? And the ImageNet models are a little better when tested on COCO or ImageNet, which are more within distribution for those models. But roughly across all the data sets, it's quite simple. When examining the models, we find that common categories can be constructed from unsupervised features. So what we're doing here is we're taking those high-level 700+ features, and we can get what's called a class activation map. We can look at the attention map for each of those different features. And then we can weight those attention maps and sum them, weighted by how relevant they are for a particular category, when we try to just tune those weights. So for the score for cat, right, is just the sum of the weighted features, and we're going to use those weights to reweight the attention maps. And when we do, you can see that it is a decent cat localizer in images. Right, so here's the cat, and this is where the model is attending. Now, sometimes it attends like the area around the cat, or maybe the cat's favorite spot, even if the cat isn't in it. Sometimes it gets part of the floor with the cat, but it largely, focuses in the right places in the image. Same with car. It's quite good at localizing cars, but sometimes it also picks up some of the road around the cars. We can also look at global category structure. But what we're going to do here is we're going to take the prototype of each of the classes in ImageNet, which is totally out of distribution for the baby trained model, right? We're just taking those fixed features, and we're going to compute the prototype of each of the ImageNet categories and do a t-SNE embedding. And what we find is that it's largely taxonomic, the global organization on the right side. Again, we can't get into the details. We have the artifacts on the left side. We have the living things. Here are all the dogs that I've been mentioning in ImageNet, but we have birds and mammals and reptiles and insects, and some food is kind of in between the artifacts and the animals. So it makes me wonder whether a special taxonomic bias is really needed for word learning, say for 2 and 3-year-olds, which would be at the later age point that's represented in the data set, where this taxonomic structure emerges from the visual experience and self-supervised learning. Now I'm going to tell you about the associative learning piece here, which was covered in this paper by Wei-Qin Wang. You can email me for a preprint. Hopefully it will be published soon. So to borrow a phrase I heard from Dilip George, it's under minor revision in a major journal. I'm happy to share the preprint. And this is about that associative learning. So now we have those visual features, and we want to see if we can map it to the real language that the child was hearing sprinkled over that 2-year period. The Wei-Qin developed the CVCL model for child's view for contrastive learning. This model is a lot like the CLIP model, if you're familiar with that architecture from OpenAI. And what we're going to do is take that pre-trained self-supervised vision model and use that to process images, just like we did in the model I just mentioned. But we're also going to have a simple verbal encoder, which is going to take utterances that were uttered at the same time a video was being processed by the child as well, and encode that as a vector as well. And just want to point out the limited data. It's 61 hours of video that has annotated utterances. So it's less than 1% of the child's waking hours over that 26-month period. So it's really only just snapshots of what the child gets. So in reality, they really got a lot more data than as well. So what does the associative learner aim to do? Well, it wants to learn how the visual world corresponds to verbal utterances. So if this frame was paired with, look, there's a baby, we want to get the vector for the utterance and for the image to be rather similar to each other. And we're using cosine similarity here. And if this image was paired with, now it's a big ball, we want those vectors to be more similar to each other. So those are going to be the attractive forces in the model. But there's also going to be repulsion forces. So we can create mismatched pairs where you pair an utterance with frames that it did not co-occur with, and you want to push those to be more different from each other. So if you're familiar with like the family of losses in the machine learning literature, this is the info-NC loss. But to make the connection for cognitive development, it's really and since we have Chen Yu here, it's cross-situational learning in a way at scale from natural experience, right? As we're tracking the associations between visual content and the words that are uttered and doing it in the room. Let me tell you about how we evaluate acquired word referent mappings. We're going to see if this model has picked up any words. And here we have no linear decoder on top. The model itself is learning mappings between the words and utterances and the visual features. And we're going to use the same type of evaluations that's often used to test children's vocabulary. You can have a display with a prompt like which one is the ball and 4 different options. So here we're using the labeled subset of the headcam data with 22 categories like ball and crib and sand and stairs. You can see there's a lot of variability visually. I'm going to construct these four-way classification trials. In terms of CVCL, how does the model perform this task? It's quite straightforward. We pass each of the four options through the visual encoder and get a vector. And then we can take the word ball, get its embedding, and we can see which of the images is the best match. Now, importantly, there's no decoder, there's no fine tuning, there's no strong supervision, there's no direct labels, right? It's just seeing if it's picked up the right sorts of associations when trained on slices that of the ABS's experience. And what do we find? We find that CVCL can indeed learn word reference mappings from real data. On these four-way classification tasks, the model is at about 61.6%. And the error bars here over different runs of the model. The y-axis is classification accuracy, and chance is 25%, right? To put this in perspective, we can look at some lower bounds. So say we break those associations. We have the same visual and language information, but we scramble what they're associated with. Now the model falls to chance in that shuffled scenario, right? Or if you train with random features, rather than the pre-trained self-supervised visual features, also performance is substantially worse. We can also look at some upper bounds. So we can take CLIP, which is a web scale model trained by OpenAI, trained on 400 million image text pairs from the web. Now this has got an outer distribution problem for it, the baby head cam data. And interestingly, in this outer distribution setting, it's about the same performance as the CVCL model, just a little bit better. That's an interesting comparison. And we take the approach on the previous paper where we're going to train that linear decoder on top, but with unrealistic labeled supervision, right? Then the best we can do is 81% correct. So that you can think of those as like different upper bound comparisons. And you could break down the results by category. And interestingly, the best categories for CVCL are things like sand and crib and car and paper. And the hardest ones are like toy and basket and room and hand. It doesn't necessarily correspond to age of acquisition for children, so we can talk about that in the discussion. That would be interesting. Word frequency is also not a major factor. I can tell you about what we have learned about why some words are picked up easier than others in this learnability experiment. Right? It's not necessarily modeling the exact process children would come to, but it does show strong abilities to learn certain words from the environment. It's also learned a flexible multimodal representation space. So here I'm showing you a T-SNE embedding of a large set of baby head cam frames. And I'm going to highlight across all these frames some sand images that are have gold labels on them for sand. And with CVCL, we can also predict the 100 frames that are most likely to be sand, that are most similar to the sand word, right? And you can see it does a good job grabbing the same region of space and many of the same images. And we can also look at the substructure of the category. And notice there's a cluster up here which corresponds to sand at the beach, and a cluster down here which just emerged for sand at the playground. For stairs, these are the gold labeled frames for stairs, and the CVCL predictions are also pretty close. There's a cluster for the outdoor stairs leading up to the baby's house, and a cluster for various indoor types of stairs. For puzzles, there's a cluster for their favorite letter puzzles and a cluster for the other puzzles. So it's worth noting that if you think about like the word itself is just a single vector, like a prototype. But a prototype model in cognitive science doesn't represent substructure, like multiple clusters. That's actually something that has been discussed a lot in the category learning literature, often has to be built in explicitly into models. Here it emerges for free in this self-supervised associative framework where we get this emergent subclusters from the categories. Let's examine generalization to completely new visual examples. So we can use Talio-Konkel's data set of these nicely segmented objects that look completely different than the data that the child was trained on with these white backgrounds, and they're nicely centered and clear. And see if the model has any ability to transfer to this data set without any fine tuning, without any adaptation. So there's categories like firefly and bucket and button and spoon. So this is called outer distribution or zero shot in sort of the literature around like this clip style models. And the overall performance is weaker, but still well above chance, about 35% correct. And I'm going to highlight some of the best and the worst categories, and we can talk about them. So one of the best categories here in terms of performance is butterfly. Bucket is pretty good. Button is okay, and spoon is quite poor. So let's dive into those. And what a really fascinating thing we can do is we can actually compare the examples the model got while learning from the baby's visual experience and real utterances, and see how it's able to generalize to the test images. Because there's actually, the word butterfly was only used 23 times in the data set. And you can look at what was going on, and you can see that it's not a lot of real butterflies, or if so, they're kind of indistinguishable in the camera. But it's like books where you have these nice clear pictures. So that's actually why butterfly is a pretty reliable class. And actually the butterflies that have the highest performance in terms of like the best score look more like the ones that were in the child's toys than say some of the other ones that were worse. For buckets, the child usually plays with these fun, colorful buckets, but in terms of the data set is mostly these rusty work buckets, but there's still some generalization. Thankfully, the child isn't playing with these. Buttons is kind of interesting because, again, the biggest images are like from books, but also like buttons on traffic lights. And you see it can struggle with some like unusual buttons here, but is like better at the more typical buttons. Spoons just turns out to be very challenging. It's not labeled explicitly that often, or whether it is, there's a lot of other objects in the scene. They're also very small, and spoon, although the frequency is higher than the other categories, right, it is pretty low accuracy. And I'm just going to briefly mention this and move on to the second debate. But we also find coherent global structure and alignment across modalities. We can look at whether it's learned this global alignment between the verbal input and the visual input by comparing the word embeddings in the same t-SNE space as the visual prototypes for these 22 different categories, right? So the verbal embeddings are here in blue, and the visual prototypes are shown here in green, and we have lines connecting them. And if they're closer, that means those categories are well aligned. So a very well aligned class would be crib, or stairs, or sand, and a very poorly aligned class is hand. And it turns out that this alignment is predictive, right, of how well the model is able to classify those particular objects. And we'll come back to this in the questions if you want to talk about more details about why some classes are harder than others. But to summarize this debate, right, using head-mounted video recordings from a single child, 61 hours of video over 19 months, we can show how a deep neural network without strong inductive biases can acquire word referent mappings from tens of examples, generalize to novel visual reference in outer distribution settings, and achieve multimodal alignment. Thus, a real start on word learning is achievable, but the modeling and the data are still quite limited compared to the child's experiences and capabilities. Also would love to talk about that in the discussion. But we're not at 2-year-old learning, word learning yet, and to get there, more research is needed, and we'll see how far this approach can really go. Well, let's move on to debate number 2, which is going to be about, can neural networks capture human-like systematic generalization? And it's been 35 years since Fodor and Poligin's article that launched a truly lively debate regarding neural networks and systematic compositionality. So here's the article, Connectionism and Cognitive Architecture in 1988. And as a credit to their foresight, this debate continues today. It's a rather influential article that is still talked about quite a lot. And here's my restatement of Fodor and Poligin's systematic compositionality. It's this algebraic ability to understand and produce novel combinations from known components. Of course, many others have written about these abilities in the mind in terms of thought and language, syntax and semantics, like Chomsky and Montague and Partee and Marcus and many others. But Fodor and Poligin made this strong argument about the difficulties that standard neural networks have. So I'm interested in just not whether we have this in principle, but what the behavioral consequences are of systematic compositionality. And I'll give you an example. I can give you a little live demo of like learning a new word, right? So say this is how you DAX, and I give you a demonstration. So, okay, I'm DAXing. So can you DAX twice? Feel free to do yourself if you like, or DAX while jumping, or thank you, Doctor. Wonderful DAXing. DAX wildly around the room. So due to your compositional skills, you can understand and produce appropriate actions for each of these different instructions. And Fodor and Poligin argued that since neural nets don't have this type of systematicity, they struggle with abstract rules, they're not a viable model of the mind. They're not viable as models at the cognitive level. And Fodor and Poligin's case against neural networks was, as I said, quite prescient. It's been sort of revived in recent years and investigated with state-of-the-art architectures, things like LSTMs and transformers, to see how they perform on systematic generalization with all the advances that have happened for neural networks in the last 35 years. Here are a number of different benchmark tasks studying systematic generalization that have been proposed. I've been involved in some of them, especially SCAN and GSCAN. And the principal finding across all of these is regarding neural networks is that they're still not systematic after all these years. So Marco Ambroni and I endeavored to see whether we could unlock additional capability in neural networks for systematic generalization. And this work was published about a month ago in Nature. But what are we after? What are the goals of this work? In order to address this debate, we wanted to conduct some behavioral studies comparing humans and machines side by side on the same test of systematic generalization, which I think is importantly needed because a lot of this lively debate, the back and forth has been about thought experiments or what people in principle could do in terms of their language abilities. But there's been less in terms of direct behavioral data about the successes and also potential failures or limitations people might have in their systematic generalization. So we want behavioral tasks where we can pair people and machines side by side. And then to propose a new method for advancing the compositional skills of neural networks through practice and allowing them to match human behavior. And that was the goal of this work. And I want to jump and tell you about the behavioral studies, and then we're going to talk about the goal. So here's our test. Like in the DAX example and a few slides ago, right? Suggest to people we're compositional learners, but that's a thought experiment too. And we wanted to do a real experiment. So here we have a few shot learning task that looks like this. We gave people instructions in a pseudo language of pseudo words. You get an instruction like a DAX, and then you had to produce an abstract response, like a series of these abstract outputs, which were different colored circles. So DAX was red, lug was blue, ZUP was yellow, WIF was green. And then there'd also be compositional instructions like lug, blicket, WIF was blue, green, blue. That was the right output. WIF, blicket, DAX was green, then red, and then green again. And then participants would get a query, like a new command. How do you DAX, blicket, ZUP? I'll give you a moment, think about it. If you think you know the answer and you want to shout it out or type it in the chat, be glad to get your participation. What do you think DAX, blicket, ZUP means? Any guesses? Usually at least one volunteer.
I just gave this question to Guru on Monday, and
okay.
mostly got it.
Most of them got it. All right.
We have an answer in the chat.
Said red, yellow, red. Thank you, Christian. Yes, that is exactly right. So blicket here means that you do the first thing, then you do the last thing, and then you do the first thing again. So blicket is like a function rather than having a direct output. So when you lug, blicket, whiff, you blue, then you green, which is whiff, and then you lug again. So DAX, blicket, ZUP. You DAX red, ZUP yellow, and then you DAX again. And here's the complete set of training and test stimuli that participants got in the experiment. So there were primitives and functions and compositional functions, and this was all the study information that they practiced. And then there were test queries that required systematic generalization, applying a function to novel input variables or composing functions together in new ways. So like in the DASK example, you just one example and you have to use it compositionally. You'll notice up here is only presented in isolation, but it's probed a lot at tests. So that's part of the logic. And the design of behavioral experiments, we have the four primitives, dax, lug, width, and zup. We have the modifier fep, which is like thrice in a way. So if you dax fep, you dax, 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 or red, 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 or blue, blue, blue if you lug fep. Blicket is the one we talked about, a bit like surround in a way, and kiki is a little bit like after, where if you dax, kiki, lug, first you lug blue, and then you dax, which is red. And there are no scope ambiguities, so they had a well-defined order of operations. And the instructions, all we told people was that learn a set of commands and their corresponding outputs. And they generated the outputs. It wasn't multiple choice. They had to grab different colors from this pool and drag them into place to produce the right outputs for the test items. There was curriculum learning where you started with the functions and then built up to the compositions, and that improved performance. And they got the study item visible during the test phase, so they didn't have to memorize all the mappings. It's rather hard to keep all of the colors straight otherwise. And participants were recruited on Mechanical Turk. So here was the overall level of performance. People were on average about 84% correct for applying a function to novel input variables. And in terms of composing functions together in new ways, they were about 76% correct. And notably, if you train a sequence to sequence, like a machine translation model from scratch on this task with 14 training examples, it's not enough to train a standard neural network. Performance is almost at floor, it's close to 0%. And I also tried to see whether we could get GPT-4 to do this. And I tried lots of different ways. And the best performance I could get out of GPT-4 was 59%. So substantially worse than people. And is very fragile, depending on the order of the items and all sorts of details. Performance could be much lower than that. So let's zoom in on one of the functions. Okay, dax, blickets up. This is the one we did together as a demo, right? Red, yellow. So 85% of participants got it right. What's also really interesting are the errors that a lot of participants made mistakes like the following. They'd go red, green, yellow, where red, so they said, okay, I think dax is red, and I know zup is yellow, so I'm gonna align those. And blicket, what's a blicket? And then they kind of pick one of the colors that blicket aligned to previously. Although blicket was actually a function, it doesn't have a specific meaning, right? So we're calling this a one-to-one bias. There was a tendency to try to translate in like a one-to-one fashion. Another example, this is a compositional instruction, right? With kiki, zup, fep, a test item. So what you should do here is first you zup fep, because with kiki, you got to do the last thing first. So you need to do 3 zups, or yellow, yellow, yellow. And then you go back and you whiff, which is green. 85% of participants got that right. But a representative mistake was to forget to switch the order. People didn't like to learn functions where the last thing, they had to do the last thing first and the first thing last. They wanted to do the first thing first and the last thing last. So there's some type of iconic concatenation bias, which I think also has some parallels in natural language. So the successes were quite impressive, but the people were far from perfect, and there was a lot of structure to their mistakes. But to summarize, there was this tendency to try to map one word to one symbol, not one word to two symbols, and iconic concatenation, first in, first out. So if you knew dax is this and zup is this, dax, zup, people naturally just wanted to concatenate them like that. And we can talk about the parallels for these abilities and how that might relate to natural language, like how it's easier for children to learn certain connection words, or how this might relate to like the whole object bias in word learning. In the second experiment, which I'm just going to breeze through in a second, we wanted to investigate these biases further, and we had a rather extreme open-ended compositional generation experiment. We said, okay, a participant, same deal. You get commands, or goal is to guess their outputs, but you know what? We're not going to give you any information about how to do the task. You have a worksheet, and you need to just guess what zup might be, or zup zup, or dax zup. There's no right answer, no wrong answer. We're just interested in your intuition. And again, they have this pool of items. And despite the completely open-ended nature of this task with no training examples, so you can't like ask a neural net to do something with no training examples, people showed highly structured responses. Almost 60% of participants responded in a way where they showed 3 inductive biases, the two I talked about in the mutual exclusivity bias, where they wanted to map a unique output to each of the inputs. So they would say, okay, green, if FEP is green, then FEP must be two greens, and FEP width must be green and then yellow. They choose one color for one word, and they did a first in, first out ordering, and they kept it consistent across all items. So that's what most people did, but there was also other instances. Here's somebody who basically did that, but they mapped the number of syllables in the words to the number of colors for each of the words. So here's somebody who did something a little bit more unique that's harder to describe. So you can look at the papers if you want all those details. But those are the two experiments, and I want to talk about the modeling in like the last 10 minutes or so. And talk about this new method for advancing the compositional skills of neural networks through practice. And tell you about meta-learning for compositionality, or MLC, which is this method to advance compositional skills of a neural network through practice over a series of episodes. So in an episode, MLC, or a neural network like the same transformers we were talking about in the first debate, are going to get a new word as a study example, and they're going to be asked to use it compositionally. And then they're going to evaluate themselves and how well they did that, and then move on to the next episode. So to make that concrete, passed as input to the transformer is going to be a number of things, a new word like skip, and some other relevant examples like how to jump twice and how to jump. And then from those study examples, it needs to try to answer the question, how do I skip twice? Again, assuming skip here is a new word or has a new meaning. And then the output is whether is the actions needed to skip twice. That's going to be compared with a target, and the network is going to try to improve. And then at the next episode, a new word might come along, like you get introduced to the concept of tiptoe. And you also get some relevant study examples. All that's passed as simultaneous input to the transformer, a bit like a prompt. And now the model wants to try to see if it can tiptoe backwards around the cone, reusing pieces of the existing knowledge. It gets evaluated and tries to improve. So that's the basic idea. And how does this ground out in that few-shot and structured learning task that we tested with people? Here, the meta-learning proceeds over a series of compositional tasks, each with a different latent grammar. So you can get different episodes, each of which is going to have a different series of compositional rules. So episode 1 might look like a bunch of these pseudo words and outputs, and it's going to have a latent grammar, and there's going to be questions that the network is going to try to answer. They never sees the grammar, right? It has to try to figure out those rules implicitly and then answer the questions. And then it's going to improve, try to do episode 2 where it gets a different set of inputs and questions, and it'll try to improve its compositional skills at learning rules. Now, the targets for the queries are both based on the grammars and sometimes based on one of the 3 inductive biases that I mentioned on the previous slides that people had. So we alternated whether the outputs were based on one of those 3 biases that was observed empirically or the grammar. And now we want to see if that captures what human abilities. The caveat here is that we're trying to get to this adult level compositional skill on these types of tasks, but we're not necessarily keeping fidelity to how people might actually acquire these skills. And we can talk about how to make this training procedure more realistic in the discussion, but that's a correct caveat. But after meta-learning, how do we evaluate the model? We're going to give it a new system of rules that is completely new, right? The model never got during meta training, which is the same one that we tested people on. And now that the transformer has updated its weights and they're completely frozen, so it has to try to learn this system of rules from just a few examples and use them compositionally using all frozen weights. So it's not allowed to update its parameters. And also try to prefer certain input-output regularities that participants also prefer in terms of one-to-one and iconic concatenation mutual exclusivity, right? So we get a query input like DAX Blickets up, the one we did as a demo. The network is going to try to produce the right output, and it gets those study examples provided as context and simultaneous input to the transformer. It's been trained to try to induce rules and use them compositionally through its meta-learning. So how do people in MLC compare? After meta-learning, MLC's most likely outputs are perfectly systematic on this task, 100% consistent with the grammar if you generate just the most likely responses. Now, if you do stochastic sampling over the responses, MLC's accuracy is close to human performance, 82 versus 81, so pretty close. And in terms of predicting human responses, in terms of the successes and failures, the best thing we can do is compute the log likelihood of the human data given the model. And if we do that with just randomly picking colors, we get this log likelihood. Now, larger numbers are going to be better. And the best model in the model comparison is the MLC model. But if you just try to train a standard neural network on this task, and no other task, it's rather poor, as I mentioned. We also tried to engineer symbolic models, like one that has an oracle knowledge of the real grammar. And that's not a great fit. If you have an oracle knowledge of the real grammar and you try to engineer the inductive biases, you get close, but still not as good as MLC, which captures some other subtle patterns that that model does not. So it's the best account of what people did in our model comparison. There's other comparisons in the paper that I don't have a chance to tell you about. Just to give you some examples, but this is that demo trial we did together, and you can see for the human responses, some people did those one-to-one mappings instead, as I mentioned, or color substitutions. And the model, again, in parentheses here is how many people produced each response. So 21 people that produced a dominant response, and the dominant response for the model in terms of frequency of responses is also the right answer, but it produces one-to-one errors as well, like people. In terms of ZUP, Kiki, DAX, where first you should DAX or red, and then you should ZUP or yellow. The 19 people got that right, but there is a concatenation error and a one-to-one error. And the model, again, also makes similar types of mistakes in terms of forgetting to do the last thing first and the first thing last. One more I'll just flash up here is one of the more complicated queries that involve 3 different functions and a reversal. And this superficially, you see that the model mistakes do resemble aspects of the human mistakes as well. So also just to mention the open-ended task briefly, you can train MLC to do that task as well, or both tasks together. So if you take a subset of the participants and train MLC on the open-ended task and then evaluate it on the other participants, where you give it a new open-ended worksheet and ask the model to fill in that worksheet, just like participants with no direct training data, just it's meta learning. How well does it produce the types of responses that people do? And again, in a model comparison, it produces roughly the dominant pattern in terms of the 3 inductive biases is roughly the same number of times as people do. You can analyze it in terms of all 3 inductive biases, which are pretty similar to people, and it's the best in the model comparison as well with the other approaches. In terms of the responses, I'll kind of skip through this, but it has both the highly structured responses and some other interesting responses that don't exactly follow the 3 key inductive biases. Okay, I'll also just want to quickly mention that in the paper, we applied the same basic idea to various machine learning benchmarks for systematic generalization, the SCAN benchmark in particular, which I also developed with Marco Baroni in 2018, where the idea is much like in that illustration of MLC, where it's like, how do you jump twice given you know how to jump, or skip twice given you only know how to skip? You pass in examples of how you do various things twice, along with the isolated new word, and then ask the model to try to jump twice. By doing meta learning, where you have practice with some permuted versions of the meanings of these words, can lead to massive gains on these systematic generalization benchmarks. So again, this is just at the high level, so you have to check out the paper. But if you take the standard neural network model, the same sequence-to-sequence transformer, but with no MLC, it's catastrophically bad in terms of error rate on various scan tests, 3 different scan benchmarks. So trying to add in the jump word and use it compositionally, it almost misses every single example. So the error rate's almost 100%. But MLC is almost perfect. So a massive gain in terms of the error rate. But the round right split for scan, it's another 1,000-fold gain. Opposite right is a major improvement. And on a different benchmark, COGS, which we didn't develop, it also dramatically improves performance 7-fold compared to a model with no value. So now I'm just gonna start wrapping up with some concluding thoughts. I'm gonna step back and look at where we are. MLC allows neural nets to do few-shot induction of primitives and functions and compose them flexibly and algebraically. It prefers hypotheses that capture certain input-output regularities in meaning, and it models adult compositional skills. But in terms of the limitations, the open questions, where we're going next, is one thing we want to know is how the model could learn entirely new primitives rather than new primitive mappings. Right now, it needs experience with all the tokens in the set, at least in some way. And we can talk about ways to get around that limitation, and we have ideas. And I think most interestingly is how did these abilities develop? I mentioned that training procedure has like more targeted data than people would be reasonable to assume they get. But can these abilities develop from realistic experience? And can MLC succeed? Can you do meta learning on the types of natural word learning experience that was discussed in the first debate of the talk? And I'd love to talk with you about how that might work and whether children are doing something more like meta learning than the types of standard training that large language models do. To wrap up, we talked about two classic debates in cognitive science and what deep learning has to say about them. In debate one, we talked about what ingredients do children need to learn words. And what the results showed is that deep neural networks can make a genuine start on the naturalistic word learning problem with only relatively general inductive biases. And those key ingredients were the data itself, the representation learning, and the associative learning on top. Other inductive biases clearly play a key role in children's smart inferences, and maybe they're more advanced word learning from 2 and up, but they may not be essential for making real progress on those initial stages of learning the words of children's native languages. And in the second debate, can standard neural networks capture human-like systematic generalization? Yes, they can, if they're trained with the right sort of practice. So here we use behavioral studies to compare humans and machines side by side on the same test of systematicity. People were highly systematic, but not perfect, and used inductive biases that sometimes help them learn, but can also lead them astray in terms of their errors. In the model comparisons, only MLC could achieve the right combination of systematicity, but also bias-based flexibility. So the right pattern of algebraic generalizations and also less structured, more heuristic generalizations. MLC can strike this balance where it learns rules, but imperfect rules. And MLC also shows how standard networks can achieve human-like systematic generalization without changing the architecture, but just by changing the training and giving them the right kind of practice. Thank you very much.